Hi, and welcome to this short concept bite video on logs. Logs are used a lot in chemistry. They occur all the time, particularly in things like kinetics and equilibria, but you'll also come across them when you've done things like pH and pKa. So, just being able to kind of handle and manipulate logs makes life a lot easier. They occur in so many calculations. So, what is a log? Essentially, a log is a function which tells you what power a base would have to be raised to get another number. That perhaps doesn't make the most amount of sense, but here I have x, my base, and I've raised it to my power z, and I'm saying that is equal to another number y. And so what my log is doing is telling me what this number z would be, or in this case, the log to the base x of y is equal to z. So this idea that logs and these powers are linked are actually very fundamental. A log and a power are what we call a reciprocal function. In other words, if they are to the same base, then they kind of cancel each other out. One does the exact opposite of the other. It's like adding 2 and then taking 2 away. If I go log to the base x of x to the a, well, that's just the same as me saying a, because that log to the base x and that x to the have cancelled each other out. And because of commutativity, I can say that x to the log to the base x of a is equally a, or in this case, straight off, a equals b. Now, the most common bases we use are 10 and e. They're so common, they have their own dedicated buttons on your calculator. And what you'll find is on almost every calculator I've ever seen, they're the reciprocal function on the buttons. So you've got 10 to the and log, and you get between them because one is shift to that same button. And so they're the most common. So log to the base 10 is so common it's sometimes just written log as in log. Log to the base e, again, is so common it's sometimes written ln. This comes from the fact that we often refer to log to the base e as a natural log. And so when somebody talks about the natural log of something, it's this ln function we're talking about. Now, ln's are used normally when we're doing kinetics and equilibria. Log to the base 10 normally when we're doing pKa and Ka. Now, you can have logs to any base, but any base would always have, any other base would always have that number as a little subscript after the log. And so here I've given the example of log to the base 2, and that would just be 2 to any given power. So part of the reason that logs are so useful is because we have some rules about how we can combine them and how they behave with each other. So first off, the log to the base anything of 1 is always 0. It could be log to the base 17 of 1, 0. Log to the base e of 1, 0. Log to the base anything of 1 is 0. My next rule is that the log of a times b is the same as the log of a plus the log of b. It doesn't matter what base I'm in, as long as all of my logs in this case are in the same base. And I have an equivalent rule, which is the log of a divided by b. This is the log of a minus the log of b. If I have the log of a raised to the power b, I can rearrange this to be b log a. And the log of 1 over a, I can rearrange to be minus the log of a. If you think about this, this final one makes sense because the log of 1 over a would be the same as the log of 1 minus the log of a. And I started this by saying the log of 1 is always 0. So just a quick example, here I'm calculating the log of 500. Well, I can say that the log of 500 is the same as the log as 5 times 100. Or I can split that down into the log of 5 plus the log of 100. Now, because I haven't written the base afterwards, I know that this is log to the base 10. And so the log of 100 in base, when I've got a base 10, is 10 to the 2, or the log of 100 is 2. So now I've simplified the log of 100 to the log of 5 plus 2. So if I actually stick the log of 5 into my calculator, I can get this 0.69 number plus 2, which means that the log of 500 is 2.69. But I instantly know that the log of 50 is 1.69, or the log of 5,000 is 3.69. Just these kind of relationships become slightly second nature to you. You can stick any of these numbers in your calculator to give it a go. Now, sometimes it's really useful to be able to switch between bases. So we've got a new rule for this. Log to the base b of x is equal to log to the base a of x over log to the base a of b. New rule. Give it an example. Well, here I have log to the base 10 of x. And this is the same as the log of x over the log of 10. And if I put in any numbers into this, just to switch between e and base 10, so my natural log and my base 10, my two most common logs, well, I can stick 17 in here. And I'm using these numbers because I can check both log to the base 10 and log to the base e on my calculator, and you can test it works. So I now have log to the base 10 of 17 is equal to log to the base e, or natural log of 17, divided by the natural log of 10. And stick all of those numbers into my calculator, and that gives me log to the base 10 of 17 is 1.203, and then the natural log of 17 is 2.833, and the natural log of 10 is 2.302. If I actually work out what 2.833 divided by 2.302 is, it's 1.230, kind of just proving that that relationship that I showed you works. I'll be back with another video which is on powers, but so far I hope this helps. Have any questions, please make sure you ask me. Bye.